Assalamu alaikum, dear students. I'll be making this tutorial to discuss a new term that is moment of inertia. Moment of inertia is a term that will be also called rotational inertia. There are different names, all indicating the same idea. In some books, I found it to be called angular mass. And by looking at all of these names given to this term or idea, moment of inertia, rotational inertia, and angular mass, the one common thing is that there is the word inertia, and inertia is directly related to mass. Now, let's go and explain the meaning physically of the moment of inertia. The word inertia, which is relevant to Newton's first law, is the resistance of an object to do motion in case it's at rest, and it's the resistance of an object to move in case it is not moving. So it's the resistance to change the state, In this new idea, the only new word added to inertia is the word moment of inertia. The word moment indicates that there is a resistance to happen. The inertia itself means the word resistance, but this resistance is not for any motion. This resistance is only for rotational motion. In other words, when I am measuring the rotational inertia or the moment of inertia, I am measuring the resistance of an object to rotate. What are the factors that affect the resistance of an object to rotate? It has been found that the moment of inertia, which is symbolized by the letter I, this is the moment of inertia. It is symbolized by the letter I, which is the first letter of the word inertia, is equal to mr squared, which means that the moment of inertia depends on the mass of the object and depends on the radius of the object. The bigger the mass, the bigger the inertia. And the bigger the r, the bigger the inertia. I will show you figures in another slide now to explain how does the inertia change with the change in mass and the change in r squared. Before I come out of this slide, let me reveal the unit. The unit of I is kilograms times meter squared. Let's take a look at this experiment that is testing the moment of inertia of these three shapes. We have the sphere as our first shape, we have the disk as our second shape, and we have the ring of which is the third shape. What they have in common is that all of these have equal masses, okay? All of them have the same m. Mass of the ring is the same as mass of the disk, is the same as mass of the sphere. So we have unified factor m. Let's take a look at their radius as well. And the radius of the three shapes is the same. The radius of the hoop is r, the radius of the disk is r as well, and the radius of the sphere is r. So now we know that the three shapes have the same m and they have the same r. If I am to compare their moment of inertia I, which is supposedly m times r squared, all of them should have the same I. I of this is the same as I of this, is the same as I of this. Since we know that I is the resistance to rotate, all of them will resist in the same way and will come down this ramp with the same speed, since all of them have the same I. Let's see what the experiment will reveal. I want you to predict if there is gonna be a difference between the speed of the sphere, and the speed of the disk and the speed of the ring, will one of them be faster, or will all of them be equally fast? Will one have a resistance more, or all of them will have the same resistance? I want you to predict before I reveal the next slide. The three objects have been put on one level on an inclined plane, and they will be released at the same time, and we will see which one will arrive first, or if all of them will arrive at the same time. This is a shot taken for the three objects as they were coming from top of the ramp to the bottom of the ramp. As you can see that the sphere was the fastest, although it had the same eye as this one, What is the factor that had played a role in making this sphere fastest? I think you're gonna say mass or R. Remember that when we started, we said all have same mass and same R. Same mass and same R. So what is the difference between them? It is the shape. The shape of this is a hollow from inside. The shape of this is filled. It's a disc. And the shape of this is a sphere. The only difference between the three is the shape, and the shape played the role in making the sphere have arriving first and having a low resistance, low inertia, low I. Okay? It's very important to understand that moment of inertia also depends on the shape. The farther the mass from the center, the more inertia it has. The closer the mass to the center, and this is the center, the closer the mass to the center, the less the inertia. And this has the least of inertia since its mass is very much intact to the center of the sphere. This makes I least and omega max. Omega, I mean by that the speed of it. So after plenty of experimentation, scientists have come to know that shapes affect moment of inertia, and moment of inertia is found using the formula mr squared only if the shape is rotating around an axis which is not inside of it. What do I mean when I say not inside of it? I mean that the axis of rotation actually is outside. Let me show you a picture to explain further. If I take a look at this baton, we call this a stick a baton, which is held by this majorette. This is called a baton, and this is a person who walks in front of a parade. We call them majorettes. So this baton has a sphere on top of it. Now this sphere is going to rotate around the hand of this majorette. So the axis of rotation actually is not in the middle of the sphere like the experiment we have seen. This sphere is not going to rotate around itself. Instead, it's going to rotate around the hand of this majorette. So in this case, this sphere will have the moment of inertia of it found through the formula I equals mr squared. Then, if this ball rotates around itself like the previous experiment I've revealed, how do I get its moment of inertia? Let's see. There are formulas for shapes. Each shape has a formula for its moment of inertia. And for each shape, as you can see, let's take this thin hoop. Okay? Hoop would mean a ring. Okay? This is a ring. Imagine that this is a ring. Not as thick as this one. Imagine that it is a thin ring. Okay? Like any ring a person wears. Okay? So it's a ring. And this is a disc. So it's a ring but this ring is filled from inside. Okay, it's full, not hollow. This I is half mr squared, while the I of the ring is mr squared, which shows that this I is less. Okay, this I is less, while this I is more. And since I know that this I is less, this means that this is gonna be fast, because I means resistance. And if there is low resistance, the object will be fast. So this disk will be faster in rotation than this ring. And this omega will be less, which means it will be less fast than the disk. And these formulas which you see here, this one and this one and this one, okay, all of these that you see in front of you are applicable only in the case where the object is rotating around itself, not rotating around someone's hand, okay, around itself, like this rod, for instance. This has an axis here, like the hands of a clock, and it will rotate around its axis. In case the object is rotating around a point outside of itself, let's take this ball and tie it to a rope, and let the rope be the hand of someone. So if it is rotating around the hand, no longer do I take this formula, I take the formula as I equals mr squared. Let's sum up in a clean slide. If I have a shape like these below shapes that are rotating around an axis in the middle of them, then the I of them is gonna be found in the table of moment of inertias. The table is number 8.1 and it is with you at page 251. While if I take a shape which is a spherical shape like this ball, but the axis of rotation is outside the object, well, the moment of inertia will be the mass of the ball times this r squared. Thank you for watching.